Well, good afternoon. My name is Ankur. I know I'm the last person standing between and everyone here and the reception to follow, so I'll try to keep my talk short, but hopefully the material will be interesting. So I'll be talking about building a multi-tenant machine learning workflow orchestration platform and focusing specifically on the security issues with this platform. So I work for Capital One. Sorry. Yeah, so I work for Capital One, so I'm required to read through our commitment to the open source community. Capital One, has made an open source first declaration in 2014. That's when we made our first contribution to the open source community. We fund a lot of conferences in the area of Python, continuous delivery, cloud native computing, etc. Our contributions to the community have been significant, and we have released more than 40 of our own software projects. We have invested for years to build the culture and governance required to be open source first in a highly regulated industry, as the financial services industry is. Okay, so with that said, we can move on to the topic of my talk. So my team is building a machine learning platform that runs workflows. And these workflows can be simple ETL pipelines to complex DAGs that can consist of like complex machine learning models for feature engineering steps and like really complex data interchange patterns on a Kubernetes cluster. So in this presentation, the content of the workflow itself is not important. I'll be focusing on running these workflows on a Kubernetes cluster in a multi-tenant way. Each workflow is containerized using a progression pipeline and executed as Docker containers as Kubernetes job. So on the top of the slide, you can see like a example of a progression pipeline that simply involves running unit tests, security scans, static code analysis, etc., on the code of a workflow, and ultimately you produce a Docker container, which is then executed on a Kubernetes cluster. And I should say at the outset that I'll be assuming like a fair amount of knowledge about AWS, IAM, which is identity and access management, and some knowledge of Kubernetes. But the concepts that I'll be talking about apply to any public cloud system and any container orchestration system. So I'll be using Kubernetes and AWS as specific examples, but they're not limited to that in any way. So the platform has multiple tenants, which can be a single user or a group of users. And each tenant runs multiple workflows on the platform with varying compute and memory requirements. And as shown in the diagram at the bottom, a tenant interacts with the platform using a microservice exposed by the platform, providing the configuration of their workflow. And then the platform then executes the workflow on behalf of the tenant as Kubernetes jobs grouped by the tenant ID. So in this slide, let's talk about some of the security-related requirements for this multi-tenant platform. So the first one is compute and network isolation. And this means that jobs running on the platform should only have a minimum set of network accesses, and one tenant's job should not be affected by another tenant's job. The second one is least privilege cluster access control. By that, I mean that a tenant's code running on the platform shouldn't be able to perform any unauthorized cluster operations. So, for example, it should not be able to read other jobs that are running on the platform or have any information about other jobs. And then the final one is least privileged data access, which means that a user code should only be able to access the data stores that are relevant to it and nothing else. So we'll talk about least privileged data access first, because this one is the most complex. And then if we have time, we'll talk about network and compute isolation and least privileged cluster access. So there are, I'm sorry. Sorry about that. Okay, so there are three pillars to least privileged data access. The first one is access to tenant credentials stored in enterprise credential storage, which are used to access enterprise data stores. So at any large company, you have enterprise data stores, for example, like an enterprise Snowflake. And access to these data stores typically require some sort of a OAuth pattern. So like you need an access token and refresh token. These credentials themselves are stored safely in a enterprise credential store, right? The second one is a data store provided by the tenant itself. So for example, the tenant may want access to their own data, which could be located on a tenant-owned S3 bucket. And then the final one is a platform data store. So this is a data store that is owned by the platform on which these workloads are running. And these can be used to, for example, store the intermediate data produced by a task in a workflow, which is then output to another task. But this data doesn't need to be persisted. And I'll provide an example of all three of these through this like a toy workflow that is shown on the right. So this example workflow shows a simple speech-to-text pipeline that uses all three of these data stores. It pulls in audio files stored in an enterprise data store like Snowflake using OAuth tokens, which are themselves stored in an enterprise credential storage. A speech-to-text neural network model that is stored in S3. And access to this is obtained using SDS credentials using an assumed role pattern. And then you run the speech-to-text model on the audio files to produce transcriptions. And these transcriptions then need to be stored in a platform-owned S3 bucket using narrowly scoped S3 tokens. So this is meant to provide an example of how even a simple workflow might require secure access to all these three data stores. So now we'll talk about accessing the tenant-owned data stores first. And before I do that, it is important to mention a security hole with naively running pods in AWS. So on AWS, each EC2 instance has this thing called an instance metadata server, which is a server running on the EC2 instance. And this is used to query information about the EC2 instance. For example, which region these instances operating in, the IAM roles attached to that instance, and so on. By default, any application running on an EC2 instance can assume any IAM role attached to that instance. This is obviously a big security hole because this means that an application can do whatever those IAM roles allow you to do. So there are many ways to address this problem. One common solution is a community contributed add-ons to Kubernetes called KIM. And KIM as shown on the second panel on the right, or I guess, yeah, right. KIM has two parts, a KIM agent and a KIM server. The KIM agent sits between applications and the instance metadata server and blocks all access to the server. So it intercepts the credential request and passes them on to the KIM server, which could be running, for example, on a master node in your cluster. And then this KIM server communicates with AWS SDS to request credentials on behalf of the application and then passes them back to the application. So that way, an application doesn't have any direct access to the metadata server. Rather, all access is intermediated through the KIM server, and that's where the access controls can be implemented. Talking a bit more about KIM. With KIM, you add an annotation to the pod definition file to indicate which IAM role needs to be assumed. And the KIM server will then assume this role on behalf of the pod and then pass on the SDS credentials. So the way we use this to ensure secure access to a tenant data store is that when the tenant onboards the system, or when they want to run a workflow on the system, at that point they provide the IAM role ARN for their data store. And at this time, they also add the KIM server role to the trust relationship for that role. Our system then dynamically injects the tenant IAM role in the pod spec for their job. And in execution time, KIM will assume the tenant's role and provide the SDS tokens directly to the workflow job. So this technique both fills the security hole with naively running pods in Kubernetes and also provides a way for tenants to bring their own IAM role in a secure way. I know this requires quite a bit of understanding of how access controls on AWS works. But yeah. Okay, so moving on to the second pillar of least privileged data access, and this is related to accessing platform-owned data store. So the context here is that jobs need access to a platform-owned data store in order to, for example, to store intermediate results generated by the tasks in a workflow. And the problem is how to provide access to this data store in a least privileged way, because this platform-owned data store, for example, could be an S3 bucket, which is also storing the results or the intermediate output generated by the workflows running by the other tenants on the platform. So we don't want the workflow launched by a tenant A to have access to the entire S3 bucket. We want them to only have access to a certain portion of the S3 bucket that is relevant to them. So I apologize again. So in this, so now I'll basically describe how we have implemented this on our platform. So the first step is that the workflow job makes a call to a workflow token endpoint, which is an endpoint exposed by our platform, passing in the service account token. So the service account is a Kubernetes concept, which is essentially an identifier for a pod. So a workflow job is running as a pod. When it needs to access the platform-owned data store, it makes a call to a workflow token endpoint and passes in the service account token. Our platform then uses the Kubernetes token review mechanism to validate the token. So token review is a service that Kubernetes provides, which lets you validate a service account token, whether or not this is a valid token, and if so, which account does it belong to. So the token review service will send back a response indicating if this token is valid and the associated tenant ID. And then number 4, the platform will then interpolate the tenant ID to create a least privileged inline AWS IAM policy. And this is important because this lets you not have thousands of policies lying around for all permutations of tenants and S3 buckets. So dynamically generating these policies using a template prevents or lets you not have to have thousands of policies lying around. So you can see at the bottom of the picture is an example of a template. So that is the policy template. And when we get a request from a tenant, we obtain the tenant ID from the token review service in step 3, and then we replace the tenant placeholder with that tenant ID to generate an actual policy. And then this policy is then used to basically obtain short-lived STS tokens, and then those tokens are then passed back to the workflow job. So this ensures that the job only gets access to a certain portion of the S3 bucket, not to the entire bucket, and these tokens, the lifetime for these tokens can be whatever we want them to be. And then the third pillar is accessing tenant credentials. So this is required for accessing all the tokens that are stored in an enterprise credential storage that are required to access enterprise data stores. So again, for example, in the example that I mentioned before, the audio files required for the workflow could be located in Snowflake, and you need access credentials for Snowflake, which could be stored in a enterprise data store like Vault. And so the problem is, how do we do that in a secure way without the job having access to the entire credential store? So again, the steps involved are very similar to what we saw before. The workflow job makes a call to the token endpoint, passing in the service account token. Our platform uses the token review mechanism to validate the token. Number 3, token review sends back a response indicating if the token is valid. For the platform uses system credentials to authenticate with the enterprise credential storage system to obtain a token. And then number 5, we use this token and the tenant ID that was returned by the token review to then retrieve the credentials requested by the job. So again, the main idea here is to introduce the platform as an intermediary between the job and the enterprise storage system, and then rely upon the Kubernetes token review service to authenticate the identity of the job, and then to access the credentials on behalf of the job, rather than letting the job have direct access to the credential store. Okay, I only have 1 minute left, so maybe I'll just quickly talk through this slide, and then that'll be the end of my talk. So this is the second pillar we talked about, which is compute and network isolation. The way we do this is to associate a tenant with a namespace, a service account, and a node group. So these are all Kubernetes concepts. A namespace in Kubernetes is the logical unit for isolating resources in a cluster, and a service account provides a cluster scoped identifier. A node group is a collection of nodes that meet a certain set of compute, memory, and storage requirements. So maybe I'll just talk about network isolation, and then I will stop. So we implement network isolation using network policies, which is a Kubernetes concept that controls which entities a pod can communicate with. And so these policies can be used to control fine-grained ingress egress controls for pods in a namespace. And using network policies, we can ensure there is no cross namespace traffic. So essentially, we associate a namespace to each tenant, and then all jobs launched by that tenant are launched in that specific namespace, and then we create network policies which controls what traffic can go back and forth across namespaces. So that way we can tightly control like what namespace, which IP addresses, for example, a workflow job is able to access on the Kubernetes cluster.
Great, thank you.
Thanks.